All right, so as Vicky said, my name is Jason Kalirai. I'm the missionary executive for space formulation at the Applied Physics Lab. Applied Physics Lab is a division of the Johns Hopkins University. And I'm not going to spend time today talking about what we do at Johns Hopkins University or pitching any type of product, but rather I thought, especially in this climate, I would present a talk on the importance of space science. I think it's something that we take for granted all the time. And there are many benefits and many reasons to study space science, and hopefully I can try and motivate a few of them today. So first, let me introduce a couple of topics that a lot of people resonate with when it comes to space exploration and space science. But these are not the core reasons why we study space science, but I still want to point them out. A great example is the annual report that NASA releases called Spin-Offs. This is a report that comes out and it talks about how all of the technologies that have been invented because of space exploration and space science spin off into our everyday lives. A great example of this is the CMOS detector that we all take for granted every day when we use our cell phones and we snap pictures. When you're doing bold space science initiatives such as trying to find water on Mars, doing that is going to require the development of technologies that are not going to be funded for terrestrial applications, but they can be applied to terrestrial applications. A great example of this is the James Webb Space Telescope, one of the biggest NASA space science programs that's ever been developed. The wavefront sensing to align the mirrors of the James Webb Space Telescope is so precise that some of the technologies invented to do that have helped us better diagnose human eyes, have improved the quality of laser eye surgery treatment, and have led to a better identification of ocular diseases. So spin-offs are a great byproduct of space science. Another one is the return on investment. NASA's annual budget is about $20 billion a year. The payoff of that $20 billion a year is several times greater than that money. There are hundreds of thousands of jobs that are supported by space science. There's a lot of money that's generated and all 50 US states are involved. More important than that, it represents leadership across the world. NASA is a household brand. And so if you look at things like the Artemis Accords that we heard about a little bit earlier, in how we pull together the international community to ensure that space is safe for exploration, the global alliances, US innovation, these are all great examples. A really important one is engagement. The Hubble Space Telescope is a great example of this. Hubble is a household brand, right? And you see Hubble populating science fiction, populating our culture. There are movies, there are books, there's literature about the Hubble Space Telescope because of its awe-inspiring discovery potential. Here's some great examples from The Simpsons, Hubble Bubble, Google page, art that's been created, and even the fashion industry has taken images from Hubble and converted them to things that are in popular culture. And you see new bold initiatives such as JWST inspiring the public, inspiring the youth, and creating a gateway for young people to come into science at a very early age. This is something that during the development of the James Webb Space Telescope, there were public outreach and STEM programs in all 50 US states related to the innovation and technology. In a way, I'd argue that some of these kinds of NASA space science missions are the epitome of STEM, right? They are motivated by bold science. They require game-changing technologies. They represent marvels of engineering, and precise mathematics is critical to the functioning of these facilities. So those are all spin-offs and return on investment and engagements that we get from space science, but it's not the true reason, in my opinion, that we should invest and we should explore space for scientific purposes. I think that's much more fundamental. So let's go back in time, and we're going to look at how studying science, studying space science, has completely transformed our understanding of who we are as a people and how we got here, okay? So I'm going to stretch out a timeline, and I'm going to ask a fundamental question: what is our place in the universe? And the answer to this question depends on when you ask this question. And at several points in human history, because of space science, we have transformed our understanding of what our place in the universe is. So this timeline is going to stretch all the way from the first civilizations to us right here at the hub, 2025 AIAA Ascend. And on this timeline, I'm going to populate a number of major events where the combination of a scientist and an engineer looking at space changed our worldview of who we are. All right, of course, we'll start with the ancient Egyptians on the timeline. The ancient Egyptians had a 365-day calendar. They knew that the North Star was very special. They used the position of the stars to guide their daily lives, to guide their calendar across the year, when to plant their crops, when to harvest them, etc. All of the pyramids in Giza have a wall that's pointed straight towards the North Star. So they knew that the night sky was special, and they knew that they could use the night sky, leverage it to guide their own calendars. Let's fast forward a couple thousand years. Some of the first Greek philosophers, some of the first Greek mathematicians also looked at the night sky, and they tried to understand what was happening in the night sky. They created theories of what we were seeing in the night sky and what it represented relative to what we're seeing on Earth. And they got some things wrong, but that's okay. They tried to take physics and they tried to take the principles of physics on Earth and apply them to the night sky. So they got some things right, they got some things wrong. Hipparchus was a key person in this. Hipparchus was an astronomer, and what Hipparchus decided to do for the first time was actually capture the data. So he built maps. He built the first maps of what the night sky looked like. He actually painted pictures of where the stars are in the night sky, and then he looked at them again and again, the next day, and he updated those maps. So for the first time, we had data captured of what the night sky looks like. And the way that he did this, of course, was to use the first telescope. And the first telescope, I would argue, is the human eye, right? Our eye works by producing an image onto a detector by reflecting light off an object, okay? The problem is that our eye is small. The aperture of our eye is small. And so you lack resolution and you lack depth because of that aperture. Nevertheless, an astronomer named Ptolemy took the data from Hipparchus and built the first model of the universe. It's the geocentric model of the universe. Very simple. Hipparchus's data shows that the sun rises in the east, it goes across the night sky, and it sets in the west. You look at stars in the night sky, the stars rise in the east, they go across the night sky, and they set in the west. Clearly, everything is moving around us. We are the center of the universe. Okay? That's a geocentric model of the universe. We're the center of the universe. So Ptolemy, 2,000 years ago, came up with that model. After Ptolemy came out with that model, astronomers basically took a time out for about 1,500 years, and we remained the center of the universe. And then it changed. And it changed only 400 years ago. 400 years ago. Think about it. The Earth is 4.5 billion years old. Civilization has been on Earth for a long time. And it was just 400 years ago that we realized, hey, we're not that special, right? We're not the center of the universe. And the reason that we realized it was because of the combination of a scientist and a telescope. The scientist was Galileo, and the telescope was the first telescope that existed. The Dutch had played with lenses and coordinating lenses to try and magnify things, but Galileo was the first person that took an engineering tool, this telescope, and pointed it to the sky. And one of the first objects he looked at is one of the brightest objects in the night sky. It's the planet Jupiter. And when Galileo looked at Jupiter, he saw a few objects that he thought were behind Jupiter, background stars. So there's Jupiter, bright object, and there's a couple of small objects behind it. And he thought, okay, well, that's just like the rest of the night sky. You know, there's an object, this object's behind it. When he came back the next day and he looked through the telescope again at Jupiter, and he compared the picture that he drew on day 1 to day 2, the objects moved. The first day there were 3 of them, now there are 2 of them. He came back the next day, he looked at Jupiter again, there was 4 of them. Came back the next day and they moved again, and all of a sudden he realized that they're not background stars. These are objects that are moving around Jupiter, and they're getting occulted by Jupiter. So when one of them moves behind Jupiter, you can no longer see it. So instead of seeing 4, you see 3. The next day it comes back because it's peeking off on the side. So Galileo concluded that the Earth cannot be the center of the solar system, let alone the universe, because there are objects going around Jupiter, so not everything goes around Earth. Okay? So after Galileo's telescope, astronomers and engineers began building bigger and bigger telescopes. And by doing that, they were able to see beyond the solar system, they were able to see into the Milky Way galaxy, and they began to look at and build kind of maps of what the Milky Way galaxy looks like and how we fit into the Milky Way galaxy. And then, about 100 years ago, there was something known as a Great Debate. If you Google the Great Debate, you would think the Great Debate must be any of a number of historical, philosophical discussions or legal battles, but no, it was 2 astronomers duking it out, trying to figure out what our place in the universe is, okay? And the question was that through the telescopes that we had built in the 1900s, powerful telescopes, you look up at the night sky and you see a bunch of stars, but then occasionally you see a fuzzy patch. And so the Great Debate was a conference where astronomers debated what the origins of those fuzzy patches were. And you can see these fuzzy patches all over the place, okay? All over the night sky. And so there were 2 theories. Theory number 1 is, it's just a cloud of gas and dust in our Milky Way galaxy, right? And we can't really resolve it, and so it's just a nebula in our galaxy. And theory number 2 is no, it's an entire island universe or an entire galaxy that's beyond the Milky Way galaxy, and we lack the clarity to see it in detail. So to answer this question about what our place in the universe is, it again took a scientist. A scientist's name was Edwin Hubble, and Edwin Hubble used a telescope, which is a 100-inch, 2.5-meter telescope at Mount Wilson Observatory, and he pointed that telescope to one of these fuzzy patches, and he discovered the distance of that fuzzy patch because he could see a certain type of star that we can measure the distance of. And he concluded that the distance of this fuzzy patch was so great that it could not possibly be in our galaxy. It was an entire galaxy itself. This is a picture from NASA's GALEX telescope of that fuzzy patch. So this is a modern day image of the fuzzy patch that we were looking at in the 1920s, and this entire galaxy, just like the Milky Way galaxy. This galaxy, Andromeda, contains hundreds of billions of stars. So again, all of a sudden, just 100 years ago, we became less special because everything that we looked at the night sky was not a part of the Milky Way galaxy. A subset of what we're looking at are entire island universes with hundreds of billions of stars themselves. So our fundamental understanding of what's our place in the universe changed because of that discovery. Fast forward from the 1920s, astronomers started understanding the nature of galaxies. We built bigger and bigger telescopes on the ground. We pointed those telescopes across the night sky, and we started to understand how our Milky Way galaxy fits in with respect to other galaxies that are larger, smaller, contain more dust, are mergers, are older, are younger, etc. in the galaxy. But eventually, we hit a roadblock. And the roadblock that we hit was that no matter how big we make our ground-based telescopes don't have the resolution and the clarity to answer the big science questions. So an astronomer in 1946 named Lyman Spitzer wrote a paper called Astronomical Advantages of an Extraterrestrial Observatory. So Spitzer postulated that the air we breathe, it sucks. It makes our images blurry, right? We need to get rid of it. If we keep building telescopes on the ground, we have to look through the air, and the air creates aberrations, and it creates fuzzy images. So the way to get around that is to put a telescope in orbit in space that would be free of that aberration, and we'd get much clearer images, and we'd be able to see much deeper into the universe. About 40 years later, we built and launched the Hubble Space Telescope. And the Hubble Space Telescope has transformed almost every area of modern-day astrophysics. Moreover, it's made the universe colorful. It's made the universe more accessible for the entire world. It's a household brand. It's an identity that everybody resonates with. Let me show you just one image from the Hubble Space Telescope. And this is an image that, again, reshapes our understanding of what our place in the universe is. Astronomers decided to turn on the camera of the Hubble Space Telescope and look in a direction of space where we see nothing. Okay? I'm going to play this video. So we turn on, we just integrate. We're just measuring photons from the universe are coming in, streaming, hitting the Hubble Space Telescope's mirror, and we point it in a place where we see nothing. And there was a debate at the time on whether we would see anything. But Hubble didn't disappoint. Hubble showed that in an area of the night sky that's equivalent to you looking up through a drinking straw. Imagine that little, tiny little postage stamp that you see through a drinking straw. There are thousands of galaxies. Galaxies of different shapes, different luminosities, different colors, different ages, different star formation histories. And so if you say, okay, well, now I know that there are thousands of galaxies in this tiny little part of the night sky, if I assume that that tiny little part of the night sky is the same all around, how many galaxies are in the universe? And the answer is hundreds of billions. Okay, so we, humanity, we are sitting on a rock, orbiting a star, and that star, our sun, is one star out of 100 billion stars in our Milky Way galaxy. And beyond our galaxy, there are hundreds of billions of galaxies with hundreds of billions of stars. So the number of stars in the universe is a 1 with 23 zeros after it. We're not special, folks, right? So again, a community of scientists using the Hubble Space Telescope made that discovery to reshape our understanding of what our place in the universe is. Next up, Hubble was great. I was a former project scientist for the James Webb Space Telescope. Hubble was built in the 1980s. And so astronomers decided we need to do even more. We need to look further. And so tens of thousands of people over 20 years, $10 billion built the James Webb Space Telescope. And a few years ago, we launched the James Webb Space Telescope, and it's been working fantastically. It's been functioning great, and it aims to take the next step in answering this question about what our place in the universe is. Before I come to that, let me show you one of my favorite images from the James Webb Space Telescope. So this is a sidebar from the talk, but I can't help myself in explaining what you're seeing here. If you look at this image, you're probably thinking something's wrong, right? It's out of focus, right? There's a bunch of streaks going across the image. Albert Einstein, 100 years ago, said that we all came up through physics and math and we learned about gravity, right? So gravity doesn't actually exist. There's no mysterious force that's pulling us towards Earth, that's pulling us towards one another. Gravity is a simplification of a concept. And Einstein said 100 years ago that gravity doesn't exist. But what's actually happening is that space is a fabric. And so imagine, the three of us are holding a sheet, like a bed sheet. Imagine we stretch it out. And then on that bed sheet, we throw a marble. We put a marble. At the location of the marble, the bed sheet's going to have a divot. And so Einstein said, stars, galaxies, planets in space are creating a divot, are creating a warp in space. And so if you shoot another marble near on that sheet, it's going to bend towards the marble because space itself is warped. Okay? And so this was tested and proven decades after Einstein suggested it. Here's an image from the James Webb Space Telescope where all of the white light that you see are galaxies, thousands of galaxies that are all packed into this tiny region of space. And so there's so much mass there that there's a huge divot in space. And all of the arcs that you see have nothing to do with those galaxies. These are background galaxies, but the light from those background galaxies is coming through space, and all of a sudden there's a warp And so the light from the background galaxies gets stretched and warped because space itself is warped in this region. And so you can use all of these arcs. A lot of these are the same, like that's the same as that galaxy, that's the same as that galaxy, right? Normally it would just be a single pinpoint, but you can see, if you take a wine glass and you're sitting in your kitchen and you put the wine glass near the table, you'll see the light from the top off the bottom of the wine glass warping around the wine glass. That's what's happening here. So you can actually use these arcs to measure how much mass is in the system. You can use them to see objects that are actually further away because normally they wouldn't be lensed, but here their light gets amplified. Okay, it's a quick sidebar. All right, so through the talk I've explained that, the Earth is not the center of the universe. There are hundreds of billions of galaxies out there. We're not that special, but maybe we are, right? The question for us in this generation, in this era, is about life, right? When you look at our planet is teeming with life. It's a beautiful world. There's no other world that we know about right now that has life on it. So on life, we would say n equals 1. But let's challenge that. If you look at planet Earth and you look at the extreme conditions on planet Earth, so for example, if you go to the bottom of the Marianas Trench, the deepest part of the ocean, intense pressure, no sunlight, frigid environments, you see hydrothermal vents pumping heat into the ocean, and you see life thriving on the bottom of the ocean floor. If you look at the Atacama Desert, there are places in the Atacama Desert that receive less than 1 millimeter of rain a year. And life thrives in those environments. Life finds a way to put itself into a state of suspension and then reemerge. If you look at the Antarctic, 200-mile-an-hour winds on the Antarctic, frigid cold, life is thriving. So no matter what extreme environment we go to on Earth, life is thriving. So the question for our generation right now is whether or not we are alone. Just like Galileo's discovery, just like Hubble's discovery, just like the Hubble Space Telescope's discovery, where we discovered that we're not that special, there's an open question, there's a Nobel Prize waiting for the combination of scientists and engineers to discover whether or not we're alone. And the universe has been very kind to us in answering this question, right? So one way that you might struggle to answer this question is if planets like Earth are rare. But it turns out that's not the case. The Earth is, when a star forms in the universe, there's a bunch of debris around it. There's a bunch of gas and dust not related to the star. And that gas and dust coalesces and forms a planet. That's what we are. Like the Earth is the debris of the star formation process. So wherever you look at stars, you have more planets. I talked about a 1 with 23 zeros because there's 100 billion stars in our galaxy and 100 billion galaxies in the universe. The number of planets in the universe is even higher because every star has multiple planets. So there's planets all over the place, and we can image those planets. We can get spectroscopy of those planets. We can look, this is an image, this is a spectrum from the James Webb Space Telescope of a planet orbiting another star in the nearby galaxy. And these absorption lines that you see here are like our fingerprint. There's an absorption line due to methane, carbon dioxide, other elements. So with the James Webb Space Telescope, you can measure the composition of other worlds, and you can look for a combination of gases that would not exist if life wasn't there. So the combination of ozone and methane, for example, is a great biotracer. What about our own solar system? This isn't an AI generated image. This is a real image of a moon in our solar system that's orbiting Saturn. And what you see here is that this moon has a subsurface ocean. And there's cracks and fissures on the surface of the moon. And so the water in the ocean is ejecting into space and raining back down on the surface. So I showed you the Marianas Trench. So we know that life exists in these frigid environments on Earth at the bottom of the ocean floor. We have the ability right now to take a spacecraft, land it right next to one of those fissures, put a cone, collect this water, and taste the water. Figure out put astrobiology experiments in there and figure out whether or not life exists in this subsurface ocean. Right in our backyard. It's Saturn. I'm not talking about like the James Webb deep fields. So right in our backyard, we can do astrobiology, we can do search for life, and also we can use powerful telescopes like the James Webb Space Telescope and its successor, the Habitable Worlds Observatory, which is being developed at NASA, to look for evidence of life on other worlds. Okay? And I think that that's the next chapter in the reward for why space science is so important. Not the ROI, not the jobs, not the spin-offs, but rather what it tells us about ourselves and what our place in the universe is, how we fit in, and how we got here. And that's the core of NASA's Science Mission Directorate and why we study space science. Thank you.
Thanks for this beautiful lecture. So I was wondering, how do you guys apply redshifted and blue-shifted light waves when it comes to determining how distant or nearby the galaxies are?
So I missed one word. So you said, how do you apply redshift and blue-shifted?
Light waves.
Light waves, wavelengths, yeah. Yeah, absolutely. So the universe is expanding, and so you and I are actually getting further apart from one another right now. It's small on small scales, but on large scales it's huge. And so what happens is, as the universe expands, everything in the universe stretches out. And so light has a certain pulsation, a certain wavelength. And so blue light has a shorter wavelength, red light has a longer wavelength. That's why when the sun sets along the horizon, it looks a little bit redder. It's because the blue light from the sun can't penetrate through all of the particles of air on our planet. The red light can. That's why the red light comes through and it shows more. So when you look at a star or you look at a galaxy, the light from that star or galaxy left that star or galaxy millions or billions of years ago, and then it has to travel through space and get to us at Earth for us to see it. So you look at the night sky, you're not actually looking at the night sky how it is today. You're looking at it how it was years ago or millions of years ago, depending on how far the object is. And as that light travels through space, it gets stretched out because the universe itself is stretched out. So if you measure hydrogen in a star, the wavelength that hydrogen absorption occurs is all shifted to the red because that object is so far that as the light has traveled through space, it's been stretched. And so you see the same hydrogen absorption lines, but you see them all shifted. And so by calculating that redshift, you know how far away that galaxy is. In the case of that Andromeda galaxy that I showed, which was the galaxy that Edwin Hubble looked at, the Andromeda galaxy is actually moving towards the Milky Way galaxy. So the universe is spreading out, but those two galaxies are so close to one another that they're moving towards one another. So when we measure the spectra of individual stars in Andromeda, they're blue shifted, right? So the lines of the absorption lines, calcium, hydrogen, helium, whatever you want to measure, they're all occurring at a bluer, at a shorter wavelength. And so you know how fast it's moving towards us. Great question. Yeah.
Great talk, thank you. I'm wondering, you mentioned about Einstein's theory with the fabric of space-time and gravity being a dent within that. For years, for millennia, we also thought the Earth was flat too.
Right.
Is there any thought within NASA as far as more of a spherical universe or anything beyond of what we're thinking about with space, gravity, time, and right now?
Yeah, absolutely. So not just within NASA, but within the space science community, there are lots of theories about the universe. There are theories about multidimensional universes. There are theories about the rate that the universe is expanding. There are theories about the future fate of the universe, whether it's going to collapse in on itself, whether it's going to continue to expand forever, etc. The point of science is that these theories make predictions. And then we use telescopes to test those predictions. And as we test those predictions, some of them get refuted, some of them get answered, some of them remain unanswered because we don't have the right technologies right now. So, for example, there's a mission that's being built at NASA right now called the Nancy Grace Roman Space Telescope. And so Roman is a mission that it's about the Hubble Space Telescope. It's the same size as the Hubble Space Telescope, the mission, but it has a camera on it that's going to reveal 100 times the field of view of Hubble. And so using Roman at the same resolution and the same clarity. So this telescope will literally image as much of the universe at the same depth that Hubble has in 30 years and 11 weeks. Right? It's crazy. And so when this mission launches in 2027, its main goal is to study dark energy. So dark energy is a mysterious force that's leading to the expansion of the universe. And the question is, what's the end state of that universe? And by measuring the positions of millions and millions of galaxies and looking at how they're moving with respect to one another, we can test and refute some of those theories about the future fate of the universe.
So my question is kind of hypothetical. So I'm wondering how the team would tackle a contamination problem with the search for life, right? Say we find some semblance of life in some location, right? How do we know for sure that it didn't come from Earth? And also, perhaps it originated from Earth, but we just didn't know that it's an organism that had already existed on Earth.
Yeah, it's a great question. So to the first part, is there's something, when we build a NASA space mission, Mike Gozeric could speak to this much more intelligently than I can, but there's something called planetary protection. So what we do is we make sure that when we're landing on another world in the solar system, that we're not bringing life to that world, we're not contaminating that world, so you get a false result because we have transported life to that world. And so when you test a spacecraft, everything is bagged up, everything is tested in a clean room. It's a very clean environment to make sure that you're not bringing the origins of life to another world. So that's an important part of how we do space exploration. To the second part of your question, yes. So if we don't detect life on Enceladus, or if we don't detect life on another exoplanet, it doesn't mean that life doesn't exist. It means that life as we know it doesn't exist because we're biased, right? But the simplest experiment is to look at the thriving life that you have here and to try and search for that somewhere else. If we're unsuccessful, maybe we need to start looking at not a carbon-based life form, maybe we need to look at different kinds of life forms. But baby steps. The first step is let's look for life as we understand it, for a future generation to start expanding the definition of what life can be.
Thank you. We'll take one last question.
Hey, good presentation. Thank you. One random question. There are some videos I've seen that show a sort of map of the universe, but there's a huge gap right around the Milky Way ecliptic where we can't see through that. So barring inventing a warp drive and traveling like 20,000 light years to the galactic north or south, what can you see through the Milky Way ecliptic?
Yeah, that's a great question. So it's related to the question where I mentioned the sunset, right? And the sunset being redder. So the plane of the Milky Way galaxy has a lot of gas and dust in it. And so because it has gas and dust in it, light that is coming from behind that gas and dust has a hard time penetrating through. So you're absolutely right. If you build a big map of the universe, there's a region of that map that you can't see through because we're in the Milky Way galaxy and there's no way we can get out of the Milky Way galaxy. It's like, imagine you lived your whole life in this room. You probably wouldn't know what Caesar's Forum looks like because you're stuck inside it. You can't get an external vantage point, right? So that's a problem that we have. Very hard to address that. I mean, the biggest thing that you can do is you can look at longer wavelengths, and longer wavelengths of light can give you some clue as to what's back there. But essentially, you've got your blinders on. There's a thin little gap right along the Milky Way galaxy where it's very difficult to see on the other side of it. Yeah, it's a great point.